Hello, everyone. This is Dr. Sharif El-Gamal, and today we will be talking about the moment distribution methods for frames. And within this video, we'll be talking about frames with side sway. In our previous video, we talked about frames with no side sway, and within this video, we'll be including frames with side sway. When do we have a frame with side sway? We will have this case if we don't have any support to support the frame from the horizontal movement or the side sway, or if the frame is not symmetrical in geometry or loading, and also there is no support to prevent any side movement. For example, if we have a frame like this, there is no support and the loads are not symmetric, the frame is not symmetric. So in this case, for sure, we will have a side sway. So when we solve such a frame, we should include the side sway in our solution. Like another frame like this, we can see this frame is symmetric in geometry. However, the load is not geometric. And again, in such a case, because of the load is not geometric, in this case, we will have also side sway. So for such frames, we should include the side sway in our calculations when we use the moment distribution method. Okay, then how can we solve or analyze a frame with side sway using the moment distribution method? This is showing the initial frame, and we know it will sway because of this horizontal force, no support here. So for sure it will sway. So how we solve this one? We solve it using two steps. The first step, we use artificial support at the top here. We assume that we have a support here, and then we are going to analyze this frame using the moment distribution method, similar to any frames with no side sway. Then we will get this R0, we'll get the value of R0, and we'll get the moment, we call it M0. Then at a second step, we are going to apply a displacement at the beam level. And then this displacement will result in some fixed end moments in the columns, in some cases also in the beams, as we are going to see in more coming videos when we have inclined columns. So this displacement will result in some fixed end moments. Then we are going to analyze this again using the moment distribution method, and we'll get moments at different joints. We call it M1, and then we get a reaction here called R1. Then we use an equation from the first case and second case to get the summation of the moment from both of them to get the final moment. But there are very important points we need to see here. In the first case, when we assume an artificial support, so all loads should be applied. In this case, the first case, we apply all external loads on the frame. Then we solve as a frame with no side sway to calculate all initial moments. We call it M0. And using the statics for the same frame here, we get the summation of force in the horizontal direction equals 0. We get the value of R0, which is this value. In the second case, when we apply the moment, it is very, very important to remove all external loads. This is a famous mistake that some people do. They forget and add loads here. So this is not correct. In the second case, we have to remove all external loads. There is no horizontal load here. There is no uniform load, only the displacement. Then we assume a displacement delta opposite to the direction of R. In the first case, we calculate the R0. So if this R is going to the left side, we apply the displacement in the opposite direction, so it will be in the right side, and vice versa. If this R was to the right, the displacement we should apply to the left. In this case, you will not get confused and will get a correct answer. You will not need to worry about direction and negative and positive and so on. Just calculate the R0, the direction of the R0, use opposite to that direction to apply the displacement, and things will go smooth. Then we have to calculate all fixed end moment due to this displacement. We'll see together how to do that. We calculate again the moments due to this fixed end moment and the displacement. We call it M1, and then we make summation of forces. You get the R1. Once we got the M0, R0, M1, R1, we can use this equation to get the moment. The final moment equals m from the first case plus r from the first case divided by r1 from the second case multiplied by m1. So m equals m sub 0 plus r sub 0 divided by r sub 1 multiplied by m sub 1. Okay, let's see together how to do that. But before doing that, let's see here how to get the fixed end moment due to displacement. Here, if we have a beam or a element fixed, and we apply displacement in one side, this will result in some bending moment at both ends. Okay, how to get that? The moment will be opposite to the displacement. This point will go up, so the moment will be in the opposite direction and will continue in the other direction with the same other point with the same direction, because this point compared to that one, it went down, so the moment will be in the opposite direction. So when you have fixed ends, you will have moments in both sides. This moment will be opposite to the displacement. How to get this moment? We can get it from the fixed end moment table, and we'll see now. But before doing that, if you have a fixed pin or fixed ruler, this is an end span with the far end is pin or ruler support. In this case, if you have displacement, for sure you will have moment only in one side, because you will not have any moment as a pin or ruler support. So how to get these moments? We can get them from the fixed end moment table. This is showing the case of fixed. When we apply displacement, this will result in moment. This moment equals 6 EI delta over L square in both sides. 6 EI delta over L square. Delta is the displacement. EI over L square. E is the modulus of elasticity, I is the inertia, and L is the span. Okay, so fixed supports, you have two moments, 6 EI delta over L square. And in the second case here, when you have an end span with a far end is pin or ruler, so you have a moment only here, 3 EI delta over L square. So you have only one moment in one side, 3 EI delta over L square in the fixed pin. And in this one, it is double the moment. And also we are using two moments, 6 EI delta over L square, 6 EI delta over L square. This is very important for the second case. When we apply displacement, it should be one of these moments. Now, how to practice that? Let's see and take an example together. And this is showing a frame. The frame is symmetric in geometry. However, we have a concentrated load not exactly at the middle. So now the load is not symmetric. So we expect that we will have side sway. Okay. So before starting step number 1 and step number 2, let's get the stiffness factors and the distribution factors, because it will be used in both steps. So let's get the stiffness factor. Stiffness factor, all of the elements here, A, B, B, C, and C, D, 5 meters, fixed, because this, if you cut it here, it will be fixed. So all of them is 4 EI over L. And because the L is the same for all of them, 5 meters, 5 meters. So it is 4 EI over L equal, this equals 0.8. Now we are ready to get the distribution factors. For the fixed ends, the distribution factor is, sorry, the distribution factor is 0 and at A and D, and the distribution factor at BA and BC equals 0.5, CB and CD equals 0.5. Why here it is 0.5? Because the stiffness is the same for all of them. So if you divided the stiffness 0.8 divided by 1.6, it will give you 0.5. So here, all the distribution factors at B and C, they are 0.5. A and D, they are zeros. So now we are ready to start with the first case when we consider no side sway. Okay, so we are going now to solve the frame with no side sway. To do that, we have to get the fixed end moments. So fixed end moments, you have member AB and CD. As there is no load, so no fixed end moments, only this member BC, we have concentrated load. So from that one, we can get the fixed end moments. It is fixed end moment BC equals W times L far square divided by the total L square. So it will be 16 times 4 square times 1 divided by 5 square. Okay. So if you want to get the moment at the other end from the fixed end moment table, there is an equation. It will tell you 16 multiplied by the far end square multiplied by the near end divided by the total length square. And this is the moment. You don't need to memorize this. You just can use the fixed end moment table to get the value of fixed end moment. For sure, here the moment at BC will be negative because it will be counterclockwise, minus 10.24. And for CB, it will be positive because it will be clockwise, 2.56. You can see here that the moment at close to the support is higher than the moment far from the support, and this is just to let you know that your answer is correct. When the load is close to BC, so the moment at BC will be greater than the moment at CB. This is 10 and 2. So now we finish the fixed end moment. Distribution factors are ready, so we can starting making our table as we used to do. We have the joint, member, and distribution factors. So in the joints we have A, B, C, and D. For the members we have A, B. Then at joint B we have B, A, B, C. At joint C we have C, B, and C, D. And then at D we have D, C. Let's put the distribution factors. At A and D they are 0. You have a 0 here and you have a 0 here. Then at B and at C all the values are 0.5. Let's put now the fixed end moment. For fixed end moment, all the values are 0 except at BC and CB. So at BC here, the value is minus 10.24. At CB, the value is 2.56. And again, concentrate when you put the fixed end moment, put them in the correct place. This is BC, you put it at BC, and then CB at CB. Once we finish the fixed end moment, then we are going to start by the joint B, get the summation of this moment. It is minus 10.24. So the opposite will be a positive value, 10.24 multiplied by 0.5 to get the value here, and multiply by 0.5 to get the value. And don't forget that the total here should be 0. We are going to repeat the same for the second joint C, 2.56. So the value here should be minus minus. So 2.56 multiplied by 0.5, it will give us minus 1.28, minus 1.28. Then the next step is to get the carryover. Let's get the carryover. The carryover, as you know, is 50% of the moment with the same sign. So we get the carryover from all the values. And don't forget that the carryover should be from one joint to another joint, not through the same joint. Okay, from C to B, from B to A, and so on. So these are the carryover. Now let's repeat the same step by doing the distribution. So minus 0.64, this will be positive, positive, multiply by 0.5 and 0.5, you get the values. The same for the second one. This is positive, so the distribution will be negative, negative, okay, and so on. Then you can repeat the same steps to get the carryover, distribution, carryover, and distribution. And then you can get the summation of the moment, get the summation of the moment from starting from the fixed end moment until the end. So these are the values of the fixed, the moment M sub 0 from the first case when we consider no Sidesway. Okay, when we consider no Sidesway, this is the first case. We got the moment, but this is not the end. After we got these moments, we called it M sub 0. We have to get the reactions that we assume. We assume artificial supports. We have to get the reaction. Let's see how to do that. To do that, to calculating the R0. So this is the first column, and this is the second column. We need to add the BC in our calculations? For now, we don't need if you have only vertical columns. Okay, but if you have inclined column, one or both of them are inclined. So in this case, you have to consider the beam BC in your calculation because it will affect the results. Okay, we will see this in a coming video with sway when we have inclined column. One or two columns are inclined, so we have to start by the horizontal beam. But in this case, if you have only vertical columns, you don't need to spend time solving the beam and getting the reaction of the beam. You can go directly and start by solving for the column. So you have column AB, which is this one, column CD, which is this one. Now we are going to put these values on the column. Okay, so MAB is 2.88 and it is positive. So this is 2.88 positive. It means clockwise. Then BA is 5.78, again positive, it means clockwise, so we put the two values here. Then let's go to the last element, the column CD. Okay, the last one, DC, which is this one, minus 1.32, minus, it means counterclockwise. Then the CD is minus 2.72, so again, it is counterclockwise. So now we need to find the reactions here, AX and DX. To find the AX and DX, it is very easy. Just take the moment at one point for the first column to get the AX. And when you have only moment, just to get the summation of moment divided by 5, the span or the length, you get directly the AX. What is the direction of AX? Always assume the direction of the AX opposite to the direction of moments. If the moment is rotating this way, the summation of the moment here rotating the same direction clockwise. So the reaction here should be in the opposite direction to make it equilibrium. Now, to find the AX, just get the summation of the moment divided by the span. It will give you the reaction, which is AX 1.73 going to the right direction. We are going to repeat this for the second column. Now, this moment and this moment is rotating counterclockwise. So the force here should be rotating to the opposite direction. So it will be clockwise. And to get the value, just get the summation of the moment divided by the span, so it will give you directly 0.81. Why we get the summation of moment and divided by the span? Because you can do the same if you have other loads or any loads here. Just take a moment at one end, and the only unknown will be the AX, so you can get it directly. When we have only moments, so it will be very easy to get the summation of the moment divided by the span. It will give you the value of AX and DX. Once we calculated AX and DX, now we have to draw the whole frame. Okay, this is the frame. Assume the horizontal reactions that you don't know here are sub-zero. Add all external loads. You have a load here. You don't have any horizontal loads, but in other cases, if you have horizontal loads, you should add them in your calculation because this will affect the R sub-zero. Okay, so don't forget if you have any horizontal load on the frame to add it in this step because it will affect your R sub-zero. Okay, so we added all external loads and the only unknown will be R sub-zero. Summation of force in X equals 0. You'll find that the R sub-zero equals 0.92 kilonewton and the direction will be going to the left. So based on this direction, we can assume now the sway. If this is going to the left side, the sway should be going to the right side. And now we are ready to go to the second step, which is the sway step. Let's see here together how to do the sway. As I explained, we have to apply a displacement called delta. The sway went to the right direction. So this is the delta and this is the delta. If you apply a delta at this point, so this element will not, the length will not change. And if you move delta, the other end will move the same delta. Okay, so let's see how to get the fixed in the moment in this case. The first case here, it is fixed. You had a delta. The second one exactly the same. So this displacement will result in some fixed in the moments opposite to the direction. Okay, these are the fixed in the moments opposite to the directions of the displacement. So in this case, how much will be this value from the fixed in the moment table? We found that this value is 6 EI delta over L square. Why it is minus? Because it is counterclockwise rotation. So all the moment will be assumed as minus values. Here, I don't need to get exactly the value. I need to get only the relationship between these values. They are all similar, so you can remove all of them. So the value here, it will be minus 1, minus 1, minus 1, minus 1. You can use the fixed on the moment as minus 1, but it will be a very small value. So you will use many digits in your table when you start making distribution and carry over. So instead of minus 1, let's get as it minus 100. So all of them we will assume as minus 100 in all of the values because they are similar. If they are not similar, so we get also the ratio. We can assume the maximum as as 100, and we get the rest from based on the ratio between them. Here in this problem, they are exactly the same. So all the fixed in the moments here, AB and BA, CD and DC all equals to minus 100 kilonewton meter. By doing that, we are again now ready to make our table in the second case. The only difference here, we are going to put the fixed end moment values that we got here. So you have the fixed end moment AB and BA, CD and DC. In this horizontal member, you don't have any fixed end moments. But again, this is because the columns are only vertical. If you have any inclined column, expect that you will have some fixed end moments here. So wait for a coming video when we have inclined columns and see how to deal with that. So once we did that, we can start making the distribution. So minus 100, this will be 0.5, so it will be plus 50 plus 50. So here plus 50 plus 50, the summation should be 0. Again, minus 100 and 0.5, so it will be plus plus 50 and 50. Make the carry over 50% of the value, so it will give you 25 all. Make again a second step, the distribution minus. Here you have 25, so it will be minus 12.5, minus 12.5, continue the same. And again, continue the same steps to make the carry over and distribution, carry over and distributions. And as I explained in an earlier video, that 4 steps are enough. So 1 step, second, third, and 4th steps. And then you can get the summation of the moment, get the summation of the moment here in all cases. These are the moments, but this value is M1, not M0. This is by mistake, it was M0, but this is the moment for the second case. We call it M1, not M0. So once we did that, we have now to calculate R1. Okay, so we will do similar to what we did in the first case. We are going to draw the 2 columns. Okay, apply the moments that we got here. This moment negative, negative, so counterclockwise rotation. And again, also for the CD, again, minus, minus, so counterclockwise rotation. And similar to what we did, get the summation of the moment divided by the span. Okay, so summation of the moment divided by the span equals 28, and the same here, 28. You can see in this way here, both of them are going in the same direction, but this is not always the same. If you have like a frame with a column going up and frame going down, you will not have the same direction. But if the columns are both in the same direction, so you will have both of them in the same direction also. Now we got the AX and DX. Let's draw a sketch of the frame, and we have now 28, 28. Don't add any loads here because this is the second case. We apply only displacement. So if you have any loads here, it will not be added in the second case. Okay. So now summation of force equals 0 in the horizontal direction. We can get R1. R1 equals, in this case, 56 kilonewton. Once we did that, we almost finished. So we have to get the final moments. For the final moments, we are going to apply this equation. Final moment equals M sub 0 plus R0. This is from the first case, divided by R1 multiplied by M1. Let's get the values from the table, in the previous table and this table, and put them, substitute into this equation. We'll be able to get the whole bending moments. This will be the end of this video. Thank you for watching. In our coming video, we'll be talking about frames with Sidesway, but we will use different lengths of columns, and also we will use inclined columns. Thank you for watching, and goodbye.